For sections 4.4 and 4.5, we're going to be talking about optimizing functions, particularly minimizing and maximizing a story problem. Now, the video that I've attached in this playlist already goes through an example like these, and once you go through this quick fact and this procedure, it's basically just a bunch of example problems. So in this video, I will be going through this fact and procedure and this story problem, and then you will have the other story problem in the other video in this playlist for sections 4.4 and 4.5. So to begin with, we have a fact that says when maximizing or minimizing a function on a closed interval, you must check the endpoints along with the critical numbers. So normally when you're maximizing or minimizing using the first and second derivative tests like we've talked about in the last few videos, you normally just check the critical numbers. But this rule is telling us that if we have a closed interval, meaning our domain is within a certain set of numbers, including the last number, the first number, or both, we have to check those values along with any critical numbers we find. An example of this would be something like this interval, 0 to 10, including 0 but not including 10, because we have a parenthesis with 10 and a bracket with 0. This is a partially closed interval. We would have to check the 0 value when we are maximizing or minimizing. Likewise, for this one, 2 to 5, the 5 has a bracket, we would have to check 5 as if it were one of our critical numbers. And finally, 3 to 12, both of them have a bracket, we would have to check 3 as well as 12. We have to check these because the first and second derivative tests only check for hills and valleys. They do not check for the endpoints of your graph. So there's a chance that your graph could have something that looks like this, for instance. Using the first and second derivative tests, we would only find this point and this point. If we were looking for the absolute maximum, this hill may be a maximum that the second derivative or first derivative test would find for us, but it is not the absolute maximum. This point is. It has a larger y value. And likewise, if we were finding the absolute minimum, the first and second derivative tests would only find this point. We would have to check the endpoint to find that this is the real absolute minimum. So that's why we always have to check these endpoints if we have a closed interval. But given these exact same graphs, if they looked like this with open dots at the end, then you could not check these values and they would not need to be tested. Only the hills and valleys would. It's very rare that this would come up, something that looks like this, where your absolute maximum is technically getting this value, this y value that's approaching a value that you can't plug in. It's not something we really need to worry about. Okay, so from there, the procedure to do this. Well, these story problems range from a lot of different ways that the problem could start off, but essentially the way that it will usually work is you need to start by constructing two or more equations based on the information provided. Sometimes this step will not be needed because it will just be given as one equation, but typically you're going to need to construct a couple of equations. And then from there you need to combine them using substitution, so plug one of them into the other to get one function of one single variable. You do this because we cannot take a derivative with more than one variable unless we're talking about partial derivatives, which would get really messy with these types of problems. So we have to get one function of one variable from all of the data by creating multiple functions and then substituting one into the other. Once we do that, we also should check if we have a closed interval. After we determine if the problem has a closed interval, we can then find all of our critical numbers. And when we find all of them, we will use the first or second derivative test to test the critical numbers. We do not test the closed interval values. Those values are automatically checked at the end to see if they provide the absolute maximum or absolute minimum. They do not need to be proven to work, which is what the first or second derivative test does. It proves whether or not the critical number is worth using. From there, we will check which critical number or closed interval value gives the desired absolute maximum or minimum value. And from there, we will finally convert the result to a sentence response. So we'll actually answer the story problem that was asked. Okay, so this may sound very long and complicated, and for the most part, it is a long process, but it's not such a complicated process. It's just once you memorize the steps, it will 9 times out of 10 always flow exactly the same way, and you'll realize the process just keeps repeating with different numbers and different equations. It is intimidating, but just take your time through it and try to memorize the pattern that's happening through all of these steps. Alright, so from there, we'll move on to this example. We have that a homeowner has $320 for a fence around a rectangular garden. 3 sides will use $2 per foot wire fencing. The 4th side will use $6 per foot wood fencing. Find the largest possible area for the garden, as well as the garden's length and width. How many feet of wood fencing will be used? Okay, so this is obviously scary. Most people hate story problems. So let's just take our time through this. The best way to generally start a story problem is to first set up a picture of what's happening in the problem. So I'll try to leave as much of the problem in the camera's view as I can. I know it's a bit blurry. So the first thing that we should note here is that we are working with a rectangular garden. Because we have a rectangular garden, we have a way to calculate the area. If we were to draw out what this garden looks like, we know that we're dealing with some length and some width for this garden. And we know that the length or the width, one of these sides will have to represent that $6 per foot of wood fencing. So we need to pick one or the other. It doesn't matter which one you pick. The problem will work out exactly the same because right now we're just literally picking which letter we want to use. So I'm going to say that the W represents the $6 per foot of wood fencing. Once we do that, that means the other 3 sides. So this is also W because it's a rectangle. Both of these opposite sides have to have equal lengths, and as do these 2 sides. So we have L and L, W, W. So L, W, and L will each have $2 per foot wire fencing, as the other 3 sides get the wire fencing. Alright, so with that, we are trying to maximize the area of our garden while keeping to a cost of $320. So, if you think for a moment, hopefully you can picture what two equations we're going to need to set up here. The first equation is probably the more obvious one. It's the area. We are trying to maximize the area, so we will need an area equation or area function. So the area of a rectangle is the length times the width. So L times W. From there, we have another function that we have to keep in mind, or another equation, and that's the cost. The cost is represented by these $2, $2, $2, and $6. But remember, these values are per foot. So to find the total cost of each side, we have to take that cost per foot and multiply it to the number of feet on each side. Meaning the cost will be, starting with the top, 2 times L plus 6 times W plus 2 times L again plus 2 times W. This represents the total cost of the rectangular garden. And simplifying, we get C equals 2L plus 2L is 4L plus 6W plus 2W is 8W. And finally, from here, the last thing that we can really make note of for this cost equation is that we have $320 at our disposal. So we should try to use all of it. Let's put that 320 in for C to get 320 equals 4L plus 8W. We want to use as much as we can to maximize the area of the garden. Alright, so from here, we've now set up step 1 of our procedure. We've created 2 equations based on the information that was provided. From here, we need to substitute one of the equations into the other. And the way we need to do that is by solving for one of our variables and plugging it into the other equation. Well, because we're maximizing the area, we need to plug the other equation into this to create an area function that we can perform the second or first derivative test on. So, to do that, we need to solve for L or W and plug it into this equation. I'm going to go ahead and solve for L. The reasoning for that is just a quick note that might be useful to you. Whenever you're solving for one of your variables, try to solve for the one with the smaller number being multiplied to it. It lowers the chances of having to deal with a fraction. So, to solve for 4L first, we're going to subtract 8W from each side, which gives us 4L equals 320 minus 8W. And finally, dividing each side by 4 to get the L alone, we get L equals 320 divided by 4 is 80 minus 8W divided by 4 is 2W. If you're not comfortable with dividing each value by 4, you could also factor out a 4 and cancel it, and you'd get the exact same result. Alright, so now that we have L, we can plug it into our area equation to create our area function in terms of one variable, W. So we're going to plug L in to get A equals L is 80 minus 2W times w, and distributing our w to each term, because we're subtracting, we get a equals 80w minus 2w squared. And this will be the function we perform the first or second derivative test on now that we've changed it to one variable. Remember up here we couldn't perform a derivative because we had two separate variables. Alright, so before we start finding our derivative, we should make one more note, and that is to find our closed interval. So if we have a closed interval, now is the time to find it. And this is a little bit of a tricky, non-intuitive step, but we need to think about each of our variables. Is there a smallest value or a largest value for each of them? So looking at W and L, do we know a limit or a minimum, like floor value, for each of them? And when you think about it, there is technically a minimum value for each of them. Neither one of these values can be less than 0. You cannot make a garden of -2 feet, for instance, on its length or width. So we have to say that this cannot be less than 0. It can be 0. The best garden you can afford might be no garden at all. So we say W has to be greater than or equal to 0, and L has to be greater than or equal to 0. As again, in each case, you could have no garden, hence the 0 width or 0 length, and you could have an infinitely large garden, which is why we need that greater than for each of them. So the W is pretty much set for us. We're getting our function in terms of W, so we want to get both of these in terms of W to see if we have a closed interval. And notice we have L is equal to 80 minus 2W. Just like we plugged it into the other equation, we can plug it into this inequality. Since L is greater than or equal to 0, then 80 minus 2W has to be greater than or equal to 0. And solving for W in this case, we're going to subtract 80 from each side to get -2W is greater than or equal to -80. Dividing each side by -2, we get W is less than or equal to +40. Remember, whenever you divide or multiply in an inequality by a negative number, you have to flip the inequality. That's why it becomes a less than. So W has to be between 0 and 40. And because there's an equal sign on both of these, we put brackets with each term. So from here, we now know that when we solve this problem, we have two endpoints on our closed interval to check. The critical numbers may not be where the absolute maximum occurs. It could be at 0 or 40. So we now perform the first or second derivative test, and I'm going to use the second as it's much faster. So to find the second derivative test, to use the second derivative test that is, we need to find the first and second derivatives. The derivative of 80W is just 80. The derivative of minus 2W squared, well, we multiply the 2 out front to get -4. We subtract 1 from the exponent, which leaves us with just W. And now we find the second derivative. The derivative of 80 is 0. The derivative of -4W is just -4. And now that we have the first and second derivatives, remember we take the top of our first derivative and set it equal to 0. Since there is no fraction here, we just set the first derivative equal to 0. Remember, with the second derivative test, if you have a fraction on your first derivative, you only test the numerator. You would not test the denominator. That's only for the first derivative test. So we take 80 minus 4w, we set it equal to 0, and now we solve for w. So we're going to subtract 80 from each side to get minus 4w equals minus 80. We'll divide each side by negative 4, which gives us w equals 20. We now need to check if this is a critical number, as right now it's just a partition number. So we check a of 20, meaning we plug it back into the original function. Our original function was 80w minus 2w squared, so we get 80 times 20 minus 2 times 20 squared. And when we simplify that on our calculator, we would get 800. 800 is a real value, which means it checks out. This is a critical number. So from here, we now just need to test the endpoints to see if either one of them results in a value greater than 800. If they do not, then we found our absolute maximum. If they do, then those values will be the result that gives us our absolute maximum. So we just test a of 0 and a of 40. Just a quick reminder, we do not need to test them in the second derivative because they are endpoints. We will only be testing the 20 value in the second derivative, which we'll do in just a moment. So a of 0 gives us 80 times 0 minus 2 times 0 squared from our original function, which leaves us with just 0. And a of 40 gives us 80 times 40 minus 2 times 40 squared, which also gives us 0. So as of right now, we have found that when we have w equals 20, it gives us the greatest value. We just have to do one quick check to prove that this is a local maximum. Everything checks out so far. We just have to use the second derivative test to verify everything, as this could be a local minimum that we found, and all the values around it could be higher, and this could be a totally messed up problem. So we always have to use that second derivative test or first derivative test to make sure. And the way we do that is we're going to take a double prime, and we are going to plug our critical number of 20 into it. When we do, the result will always be negative 4. So what does that tell us? Negative 4 means we have a concave down value. And because it's concave downward, that gives us a local maximum. So we have found the local maximum and then checked it against the endpoints, proving it was the absolute maximum. Now that we have all of our critical information, we can plug this into a sentence answer. So I'm going to move this off to the side. I'll try to keep it in the view as much as possible. So continuing on, 4.4 and 4.5. The first thing that we were checking just to move this a little bit in the view with the problem, was to find the largest possible area for the garden. Well, the largest possible area for the garden is 800, and remember our units were feet, so is 800 feet squared, or square feet. From there, it said to find the garden's length and width. So we'll go ahead and circle this for right now. We have a little bit more to calculate, which we'll do underneath here. So first of all, we found the width. W, we said, was this value of 20. That was the value that maximized the area of the garden. So W equals 20 is the width. And then the length we said is 80 minus 2W. So since W is 20, then L, or the length, is 80 minus 2 times 20, which leaves us with 40. So, to continue on with our answer, what are the length and width? The length is 40 feet, and the width is 20 feet. And finally, the last part of the problem, how many feet of wood fencing will be used? Well, remember from our picture, which I'll bring back into focus here, we said this side represented the wood fencing, and this side was one of our W's. So since this entire side is the wood fencing, then the length has to be equal to W, which is 20. So how much wood fencing will be used? 20 feet. That's a pretty terrible feat. 20 feet of wood fencing will be used. And this completely solves the entire problem. As I said before we started the problem, it is a very long process, but it is not an extremely complicated one. It's just about memorizing the steps. Always remember, going back through this in a quick summary, you want to first draw a diagram if you're able to get a visual of what's happening. Once you do that, you're going to set up whatever equations that you need, how we set up the area and cost equations, so that you can combine them, generally with substitution, to create one cost function or one area function or whatever you're working toward maximizing or minimizing. And once you create that one function, you'll use the first or second derivative test on it to find your critical numbers. You will also check for your interval to see if it's closed. And if it is, you will check your critical numbers and your interval numbers in the original function to see which yields the maximum or minimum value you're looking for. And you will also prove that the critical number is a maximum or minimum as you were looking for. Once you do that, you combine it all into a sentence answer that answers the original problem. All right, My best suggestion for these problems is to go back to the beginning of this problem, restarting the video, pause it, and then try your best to work through it as much as you can. And then if you ever get stuck along the way, restart the video and see if you can't figure it out with just 1 or 2 steps of help, pause it, and then continue your work.